So therefore, our logistic function, as defined by the variables a, b, and c, would be f of c, or f of x rather, is equal to, since our ceiling, our upper bound, or the maximum, the restraint is 1000, over 1 plus, our a is 10.0106, and our b is 1.0721 raised to negative x. So this is our function. Okay, let's make it clearer. So I'll put it here. This is our logistic function. Letter B, plot the graph of the logistic function from 0 through 100 months. Sketch the result. So without sketching all from 0 to 100 months, actually we have already sketched the graph of that function, and that function is actually the function that we took from the very beginning, and this is the same table, and so we will have the same graph like this. Okay, so meaning our graph then would be something like this. Okay, so from 2 months to 100 months, you will have a graph that behaves like this. So first it is exponential, and then it levels off, having the concavity downwards from beginning from its point of inflection, which is midway from 1000 and 0. Okay, so but let us see what is our, just for curiosity. Okay, so let us get f of 100 when x is 100. So based on our logistic function, 1000 over 1 plus 10.0106, and then 1.0721 raised to negative x. So f of 100 would be 1000 over 1 plus 10.0106, 1.0721 raised to negative 100. And with calculator with us, so let us find the value of f of 100. So our f of 100 would then be, with the use of a calculator, so I have a scientific calculator with me, so that's 1000 divided by 1 plus 10.0106 times 1.0721 raised to negative 100. And as you can see, it yields me 990.606, or around 990 houses. Okay, so there are around 990 houses, 10 houses before the ceiling, which is 1000, before the asymptote of 1000. Okay, so that is the graph of our logistic function from x is equal to 0 through 100 months. So let us just extend this to 0, so it will be like that. Okay, let's do it more accurately, but in that case, this would be, anyway, this would tend to be an exponential function, so it should be like that. Okay, so that is the answer for letter B. Letter C, make a table showing that the logistic function fits all the points closely. So first we have to write our logistic function, and our logistic function is 1000 divided by 1 plus 10.0106 1.0721 raised to negative x. Now, using our calculator again, we are going to evaluate whether or not the computed value for y with the given x. The given x is 246810. Using this function would give the same results or close values to the results to these y's here. Okay, so will our computed y values be close or exactly the same as these y values? So let's start with when x is equal to 2. So using the equation, okay? So at x is equal to 2, let us have our function. Our function is 1000 divided by 1 plus 10.0106 and then 1.0721. So let me check if I have the correct function. Yes, we do have the correct function. So if my x is 2, so I will have raised to negative 2, and this will give me 102 point, this is 102.993. So this is exact. Okay, we have exact values, 103, 103. What if my x is 4? So if my x is 4, my answer would be 116.586. So this is very close, okay? If my x is 6, that should be able to give me 131.709. So this is also very close. If x is 8, so let us see if x is 8, the answer would be 148.465. So it's still very close. What if my x is 10? So let me get the value of my y when x is 10. If x is 10, then my value for y, according to this equation, is 166.943. This is actually exact, right? So as you can see, our equation here is very accurate because it yields almost the same answer as the table. Okay? So therefore, the logistic function fits all the points closely. Some of the points are very exact. Okay? So let's go to letter D. Letter D, use the logistic function to predict the number of houses that will be occupied at the value of x corresponding to 2 years. Which process do you use, extrapolation or interpolation? To solve this problem, first we need to understand that 2 years means So 2 years means how many months? We have 24 months, right? So we are going to use 24 months for x. Okay? And what is our logistic function again? Our logistic function is again f of x is equal to 1000 divided by 1 plus 10.0106 1.0721 raised to negative x. So when our x is negative, or when our x is 24, so when x is 24, that will give us an expression which is f of 24 is equal to 1000 over 1 plus 10.0106 1.0721 raised to negative 24, of course, because our x is 24. And this will give us, so we need our calculator again. So if our x is 24, then all I need to do is to change the x with 24, and according to my calculation, my computation gives me 346.88, and this is closely 347 houses. Okay? Meaning that in 2 years or 24 months, there will be around 347 houses inside the subdivision. Okay? And what does that mean? Now, in 24 years, you have these houses. So which process did we use? Is it extrapolation or interpolation? Now look at the given table. Your given table has a range which is only up to 167. So the range is 103 to 167. And the computed value for x is 24. And in your domain also, 24 is not there. So your domain is only from 2 to 10. And the requirement is to get the value of y, or the number of houses, the population of houses, when the time is 24 months. And we computed 347 houses for x is equal to 24. But look that this 327 is not on the range. The range value is 103 to 167. Therefore, because it's not on the range, what the process that we did is getting or interpolating. I'm sorry. This is extrapolating. Okay, extrapolating or extrapolation as a process. So if your computed value is outside the range, that means that the process that we use in computing for that value is extrapolation. If the value is within the range, then the process that we are going to use is interpolation, which makes sense. Inter means inside or within those values, within those ranges, but extra means it's outside. Okay? So let's go to letter E. Find the value of x at the point of inflection. What is the real world meaning of the fact that the graph is concave upward for times before the point of inflection and concave downward thereafter? So we are faced with two dilemmas here. First, we have to look for the point of inflection. And second, we have to analyze or interpret the meaning of the the concavity of the graph before and after the point of inflection. So let's say this is our x and y axis. Okay, this being our x axis, and this is our y axis. And notice that this is x is equal to 0. In this case, this is our origin. So these are the x values. Okay, these are the y values. Okay. Now our upper bound or our limit, okay, our limit or the asymptote is 1000. So let's say our limit is there. So our limit is y equals 1000. And of course, we start from 0 months. Because from 0 months forward, of course, from time is equal to 0 months, that means it could be 1 day, 2 days, 3 days. And during those times, we are pretty sure that something is happening in the subdivision, like some of the houses are being built already, or maybe some houses are already built, okay, within those opening of the subdivision, okay. So such as in the case of pre-selling, wherein they have these model houses and they are already built. So let's take them as members of this population of houses for 0 months. So in this case, we have taken into account that the graph of our logistic function is, what is the graph of our logistic function? It is something like this. Okay? So this is our logistic function. It has a lower bound. Why is my lower bound 1000? This is supposed to be 0. And my upper bound is y is equal to 1000. And this is my asymptote. My upper asymptote and my lower asymptote. So I have two asymptotes. Okay? And the point of inflection of a logistic function occurs at the middle. So what is the middle point here? Let's say this is our middle point. It's here, okay? Let us have a representation. So this is our C over 2. Let's make it more accurate. Okay. So this is our C over 2. Right? So if this is my y is equal to C, this is my y is equal to C, they are the same. Okay? So this is my y is equal to C over 2. And this is my point of inflection. So just by getting the midpoint, we have the first point is 0, 0. That's when y is equal to 0. So 0, 0. And point, what is this one? This is x unknown. Let's say xi. And 500. What is that? Now first let us have the 2 points. So we have the C, y is equal to C, so that's x, xf, and then we have C is 1000. But our xf is also unknown, okay? So our point of inflection is in the middle of this. So this is our C, this is 0. So our point of inflection is 0 plus C, which is 1000 all over 2. Meaning that at y is equal to 500, that is where the point of inflection comes in. Okay? So let us solve for the x at the point of inflection to see or to evaluate further or to explain further why at that point this is the behavior of this graph, that after this point of inflection it tends to increase but slightly lower than when it is below the point of inflection. So what we're actually trying to get is xi, that is where the point, or let us say a more accurate interpretation is xc, because or xi, point of inflection, and then our y is 500. So when xi is unknown, our y is 500. So let's use the formula or the equation for our logistic function, which is 1000 divided by 1 plus 10.0106 times 1.0721 raised to negative x. In this case, it's xi. Let me extend this. Okay. So now I will express this xi here, or the exponential function here, as positive, so that it will be easier for us to compute for the value of x. So 500 then will become 1000 all over 1 plus 10.0106 divided by 1.0721 raised to x. Now we have a positive x or xi. And so this will give us 500 is equal to 1000 all over, we have to get the LCD of the denominator, so 1 plus, okay, so this will give us a 1.0721 raised to x plus 10.0106 all over 1.0721 raised to x. Okay? Now we will continue the solving in the next slide. So to be continued on the next slide.